Welcome to Spring LIB.
We're looking at a situation with a couple of physics steps in it. First of all, we're dropping a clay blob onto a table where there is an inelastic collision to begin with. And during that collision, we are going to have to conserve momentum so that the momentum initial total has to equal the total momentum final. So the clay blob is going to stick to the table, so its mass times its velocity initial, which is given to us, is going to have to equal the mass of the two objects stuck together. And we can then compute the final velocity from that. The second thing that's going to happen is an oscillation. So the table and clay together is going to oscillate up and down. And so we'll have to do some mechanics with dynamics of oscillating motion. And let's call that oscillation y of t. So it's going to be in the y direction. And usually you can write down a simple harmonic motion in several different ways. I am going to write it as a cosine of omega t plus b sine of omega t. That's not the only way to write such an oscillation, but it's a nice, neat way because the first term relates to an initial displacement from equilibrium, delta y from equilibrium. And the second part relates to the initial velocity of the object. And we're going to have both of these. What information they give as well is going to get into Hooke's law a little bit, but what they tell us is that the final equilibrium position happens 6 centimeters down from the initial situation. So the spring compression is 6 centimeters. Oops, let's put in centimeters. Meters, actually. That compression is 6 centimeters. And from that, and knowing the weight of the object, so it finally rests at its equilibrium position. And at that point, we know that the weight of the entire system, m plus big M times g, has to equal the spring force upwards. So that is an equilibrium situation. And the spring force can be written as the spring constant, which comes from all four legs of the table, times S. And that has to equal your total mass times G. So there's some things we can figure out, but we know that the initial position is 6 centimeters away from equilibrium. And we can determine the initial velocity from the conservation of momentum that we have going on. So let's take this one step at a time and first find the initial velocity. Okay, so that's the first thing to do. And I call it final velocity, but it's the velocity of the system after the collision. So we have 0.80 kilograms in the small mass times 1.65 meters per second is equal to the total mass. We'll just combine that right now as 2.40 kilograms. And that will give us the answer in meters per second. And it'll be 1/3 of the 1.65 meters per second. So 0.55 meters per second. Okay, meanwhile, we can go figure out the spring constant. So K times the 0.06 meters is equal to M times G. And the K should be worked out in terms of newtons per meter. And you'll see in a little bit why it's good to find K at this point. We'll go back to equation number 2, which is probably the hardest thing to kind of think through. So we get a spring constant from all 4 springs that are acting in parallel. So 4 times stiffer than a single spring, but 392 newtons per meter. Now, why we need that spring constant is you'll notice in the dynamics in equation 2, we need the angular frequency of oscillation. So let's take a little bit closer look at step number 2 with the oscillation. We're going to assume a harmonic oscillator. We'll leave out the damping and just assume the damping is negligible for the time period we're interested in. Omega is essentially the square root of K over the total mass of the 2 objects together. So we can put into that oscillating equation. We can put our angular frequency in there. And we get roughly 12.8 rads per second. Now, the other thing that I need to do is to find the constants in that oscillation that are in front of the cosine and sine term. So y of 0, if we go back and look at that, that's just a cosine of 0 plus b times sine of 0. And we know that the oscillation starts 6 centimeters away from the equilibrium. But that's not the amplitude because there's some velocity involved. Y of 0 is just equal to the A. If we take the derivative of that oscillating set with respect to time, we can relate to the initial velocity, the 0.55 meters per second. Okay, so we'll take the derivative of that oscillating function and the cosine and sine terms switch. So we see that the velocity is at time t equals 0 is actually related to the b constant. It's the initial velocity is b times omega. So we now know the initial velocity is 0.55 meters per second. And the omega is 12.8 rads per second. So lo and behold, we find that b is another 0.043 meters. So the entire amplitude is going to turn out to be the square root of the sum of the squares. So we can think about the cosine and sine term as being 90 degrees with respect to each other. And we need to add them in quadrature to wind up with the full amplitude of the motion. That can be proven with a little bit of trig identities. But we'll go ahead and use this knowledge, and we find the amplitude is a little over 7 centimeters. So yeah, we're assuming no damping or very low damping, which we know is never the case, that it's totally zero.